All right, so thermodynamics is our second to last unit that we're going to be doing. So let's recall what enthalpy is. That's from when we did thermochemistry. Remember, enthalpy is the heat change or heat exchange, and exothermic reactions are generally favored. Remember, if it's exothermic, what's the sign of delta H? Negative. Delta H negative is exo. Delta H positive is endo. That's just a refresher. We're going to be bringing something in today called entropy. If you haven't already heard of it, it's actually the disorder of a system. More disorder is what's favored because nature tends toward chaos. If we do not put energy into a system, chaos will ensue. Okay? We're getting to that in a minute. I'm just telling you what entropy is right now. Okay? So entropy is it's favored if disorder is increasing. Thermodynamically favored processes are both involve a decrease in internal energy and an increase in entropy. So just to keep things fun and interesting, if it is favored, delta S is greater than 1, or it's positive, and if it's thermodynamically not favored, due to the entropy, it's negative. So we're going to bring in something called Gibbs free energy, delta G. We're going to have some formulas to use on that. Used to be in the olden days, meaning like when I was in school, we called these things spontaneous and non-spontaneous. We no longer say spontaneous and non-spontaneous. So some of my old worksheets might say that, but I would like you to say thermodynamically favored versus thermodynamically not favored. Okay? That's actually fairly recent that they changed those words from spontaneous to thermodynamically favored. Okay, so some of your old worksheets, the ones you picked up today that I used in the beginning of my teaching career, will say spontaneous or not spontaneous. We need to actively convert that to thermodynamically favored. Okay. These processes without outside intervention would happen anyway. Okay. Thermodynamics, remember, does not take into account the rate. So just because something is thermodynamically favored doesn't mean it happens quick. Okay? And one of our classic examples is that it is thermodynamically favored for diamond to turn back into graphite, but it happens so slow that essentially it does not happen. So that commercial, the old Beers diamond commercial, a diamond is forever, thermodynamically it's actually not forever, but it happens so slow that for our purposes it is. So yeah, thermodynamics is if it's favored, but rate is how quickly something happens. Okay, so first law of thermodynamics, if it's a law you should know it, is energy can never be created nor destroyed, therefore the energy of the universe is constant. This is simply a statement of the law of conservation of energy that you already know about. Remember, it can be changed into an unusable form, but it is not lost. The second law of thermodynamics is the universe is constantly increasing the dispersal of matter and energy. And then the third law is that the entropy of a perfect crystal at 0 K is 0. Okay? There's no such thing as a perfect crystal, so this is not really going to happen. But entropy values are rarely ever 0, even for elements. Unlike our delta H values for the elements were 0, they won't be that way for entropy. This means that entropy can be determined at any temperature higher than 0 Kelvin, which is pretty much all of our temperatures. Okay? We don't need that for this unit. Okay. So here's kind of just a pictorial of your domain of thermodynamics versus your domain of kinetics. Your thermodynamics is energy difference between reactants and products. Okay. The kinetics is, what was that called at the top? Activation energy, how much activation energy is required for the rate. So that's kind of the difference. They are definitely much interconnected in understanding it, but we separate them out for purposes of learning the stuff. Okay, so what exactly is entropy? It's usually kind of looked at as chaos or disorder. The disorder of a system will increase on its own without adding any energy into the system. Nature spontaneously or thermodynamically favored to proceed toward the highest probabilities of existing. So, and that, a while ago it said the example of your room. If you can clean your room up on Saturday because your mom says, clean your room up, and you do a fabulous job, and you clean up your room, and what does it look like by the end of the week? Yeah, it's because it's spontaneously going to disorder unless you put energy into the system to clean it up. Okay? Think of an old house that sits. Think of an old house that sits and no one's in it and living in it. And even if no one's ever lived in it and it was a brand new pristine house when it was first built, what's it going to look like 20 years later? Yeah, it starts getting dilapidated, and because you got to put energy into the house to keep it nice. You can't just okay. So those are some real world examples. Here's an ideal gas expanding into an evacuated bulb. Why is this process thermodynamically favored? The simple driving force is probability, because there are more ways of having gas evenly spread throughout the container than there are for ways for it to be in any other possible state. So it just disperses into a uniform position. So let's look at this right here. How many, if we have 4 ideal gas molecules in 2 bulbs of equal volume, why are we talking about ideal gas? Because there's no, remember in an ideal gas there's no particles of attractions. So that would be all the different combinations. If you had 2 bulbs and you had 4 molecules of gas, those would be all the different combinations that could exist. Okay? It's 16, in case you don't want to count that. Okay? If you want to count it, go for it. Okay? So there's 16 different ways. So arrangement 1 and 5 each produce a single microstate with a probability of 1 in 16. That particular arrangement is improbable, so not likely observed. So that just kind of takes you through all the different possibilities and why entropy and blah, 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 yada, yada, yada. It's all on your paper. You can read, right? Let's get to the bulk of the stuff that we want to learn. So when we're predicting entropy of a system based on physical evidence, it's different if we have the values. The greater the dispersal of matter, the larger the entropy. Okay? So just before we look ahead, would you expect the entropy of gases or solids to be higher? Gases, absolutely. Okay. The entropy of substance always increases as it changes from solid to liquid to gas. So gas is your least orderly, which has the most entropy. Okay. Solids have the most order, so they have the least amount of entropy, or the least positive. Okay. When a pure solid or liquid dissolves in a solvent, the entropy of the substance increases. Carbonates are the exception. Okay. Carbonates actually interact with the water and bring more order to the system, so might want to highlight that exception. When gas molecules escape from a solvent, your entropy increases. Entropy generally increases with increasing molecular complexity. Okay, in other words, if you have KCl versus KlCl2, you have more particles, and CaCl2, because there's more electrons moving around, so you'd have more disorder. Okay. And then reactions increasing the number of moles of particles will also increase entropy. Yes?
So is entropy basically like the measure of the energy that's going on?
Not energy, order. Like the order of a system, the chaos or order. So something that's more ordered, say a crystal, is going to have less entropy than, say, that same thing dissolved in water. Okay? So it's basically disorder of a system, or order of a system, whichever way you want to look at it.
More ordered is less entropy?
More ordered is less, it has less entropy, a lower value for entropy. Yeah.
Isn't it like how much it spreads, like disperses?
Yeah, that's kind of one way to look at it. That is one way to look at it. In general, the greater number of arrangements that something can have is the higher the entropy of the system. So let's do some predictions here. We have a solid sugar is being added to water to form a solution. What is going to happen with our Entropy.
Down.
Okay. No. It's gonna. It's our entropy is going to increase because we dissolved it. Entropy increases, so we would say delta S would be positive. Yeah, because it's more. It has more arrangements now. It can be spread out, and it's moving around the container when you dissolve it or heat it, crush it, stir it. Okay. In this one, we have iodine vapor condensing on a cold surface to form crystals. So what's going to happen to our entropy there? Entropy is going to decrease. So then delta S would be negative. Okay? Change in entropy, yes. Yeah. Change in entropy would be positive for the first one, and the change in entropy would be negative for the second one. Okay? So remember the Hess's law. You can calculate entropy values from the table using basically the same equation. We just call it verse 2 because now you can do it with delta S values. Yeah. One of the things you picked up today was a table that has entropy, enthalpy, and I think Gibbs free energy. So that is not by any means all of the possibilities of compounds, but it's some of the most common ones. It should cover most of your homework when you're doing it, but if it doesn't, you might have to look some up. And you can look those up on tables, okay?
You don't have to like memorize.
Oh, Lord, no. No, that would be cruel and unusual
Yeah,
punishment.
that's why we made these tables, so scientists.
Yeah, we don't have to memorize that, yeah. And what do you notice about the values? Are there any elements on there?
Yeah.
What do you notice about the 3 values for elements?
Oh, it's 0.
Well, if it's what is delta H for an element? 0. But what is delta S and delta G? They have values, correct? Okay. Also, I want you to look at the units at the top because this is what gets a lot of kids. Look at the units. What are the units for delta H? Kilojoules per mole. What are the units for entropy? Joules. And then delta G.
It says mole K.
Yeah, yeah, but that you don't have to convert. But if one's in kilojoules and one's in joules, when we put these in formulas, are you going to be able to use them as is? No, you're going to have to convert one or the other. And what's the unit for delta G? Kilojoules. So make a little note by entropy that it's in joules, and you'll need to convert one or the other, but you cannot do kilojoules and joules together. Okay? So make sure you notice that. Okay? Because that's probably one of the largest mistakes that people make is they just use the value as is, not realizing that one's in joules and one's in kilojoules.
If you're calculating the delta S, do you have your final answer has to be in joules?
It should be. I mean, it should be.
Okay.
Yeah.
What's delta G?
Gibbs free energy, we're fixing to get to it. We haven't gotten there yet. Okay? So, calculating entropy, we know these standard values. Just pay close attention to the units, like I just said. Again, we already said this a while ago, but whenever delta S is positive is when disorder is increasing. And it's kind of funny because we're thinking of disorder increasing and disorder decreasing, which means it's more ordered, so you kind of have to get that straight in your mind. And then when delta S is negative, that is when disorder decreases or becomes more ordered. So,
Order is just a lack of disorder.
yeah, but sometimes people get that backwards in their brain, and I ran out of room. That's ordered. Okay? And then our units are joules, not kilojoules. So we just need to be mindful of that. So I think we're going to work a problem. So here we have this entropy change for SO2 combining with oxygen and SO3. So it gives us these values. So it's always products minus reactants, right? So we're going to find out what delta S for the system is. So we're going to say 2 times, what is SO3? 256.6 joules mole K. Okay. Minus, so that goes all together. And then now we need to do our reactants. So we have 2 times 248.1 joules mole K plus, I did 2 parentheses signs, sorry about that. And then oxygen is just 205.3 joules.
Do you need to put units?
You should always put units when you're doing that. It's better to put them than not put them and then get counted off for that. Okay? So we put all that in our handy dandy trusty little calculator, and we should get that delta S is equal to a negative 188.3 joules per K. So what happened to our disorder?
So it's becoming more orderly.
Disorder increase.
Up, down.
Yeah, disorder decreased, and if we go back and look at it, we're going from 3 moles of gas to 2 moles of gas, so that makes sense. Okay? Because before we had 3 moles of gas, now we have 2 moles of gas, which means it's more ordered or less disordered, however you want to think about that. So you can always kind of go back and look at it and see, did that make sense? Okay? Is everybody with me so far?
Yes.
Okay. 2 moles times that, yeah, it kind of takes care of it. Although that's also one of those units. What does it say on yours? Are they putting the moles back in there? Remember that was a change they made from the old timey like when I used to do it, that they put the moles. So it actually should be mole K. I'm looking at old notes from what is that thing called? Pre-redesign. I could not think of that. The pre-redesign, they changed, and that's also when we used to say spontaneous and non-spontaneous, and now they don't like us to say that. But I'm old, so sometimes it takes a while to teach me new tricks.
You see that in bio,
What?
the non-spontaneous.
Yeah. They may not, for them, they may not have changed it, because they don't really talk about thermodynamics a lot.
Yeah.
Although, y'all talked about Gibbs free energy. Entropy changes as they relate to reversible phase changes. Phase changes occur at constant temperature and represent a system in equilibrium. So then at equilibrium, when we get to Gibbs free energy, we'll talk about this a little more, but at equilibrium, delta G is equal to 0. Okay? So because of that, we can say that delta S is heat transferred over the temperature change at which it occurs, which is where we're getting that right there. Which means that when we have that value, if we have delta H, we can actually get to delta S. Okay? So, let's do exercise 4. Did this get left out of your notes? Hold on, let me see the next. I may have forgot to. You have this in your note that delta, whoops, sorry, I thought I said right. Delta S is equal to negative delta H over T? Is it in your packet notes? Well, that's important. It should not have gotten left out. So let me have y'all write this down, because this is going to be important for solving things. So delta S is equal to negative delta H over T.
Later on.
Oh, is it later on in the packet? It's not before exercise 4?
It is just
Exercise 3 is next.
Oh, what happened?
Exercise 4 is on page 7.
I don't have exercise 3 in here. I go straight to 4. What happened to 3? I have sample problem B, which is what we just wrote.
Do you have entropy summary?
Ooh, what happened to my notes? Okay, well, we're just gonna... Let's see what comes up. I don't even know what... I'm going off of an old one.
Yeah, there's exercise 3.
Oh, it's my exercise 4. That's weird. Okay, she must have tweaked the notes. Okay, so we have the first one, the antimony, and then carbon is the other one. So let's do the first one first. We're going to call this 1 and 2. So for 1, we know that delta S is equal to negative delta H over T. So we're going to say delta S is equal to negative of a negative 125 kilojoules per mole divided by, what was our temperature? Did it say?
25 degrees Celsius.
Okay, so that's 298 K, right? Oh, not 29 K, 298 K. How do we know we need to be in Kelvin and not Celsius? Because if you look at your units, it has Kelvin in there for entropy unit. Okay, so we will be using Kelvin, not Celsius. So we do all that math and we get, oh, that's what I just noticed. So that becomes 0.419 kilojoules per mole K, but we want to report in Kelvin, so we're going to say there are, in 1 kilojoule, there are 1,000 joules. So negative times a negative is a positive, so we have 419 joules per mole K. So what did our disorder do? It increased. So we increased disorder, right? Huh?
What did we do?
We increased disorder
But how did we do that?
because it's a positive value for delta S.
Yeah, oh, it's because. Well, I'm just wondering, like, what led to that like made it get more disorderly. Like, do we add like something?
Well, if I look at this, for one thing, we have 4 moles of solid and we went to 5 moles of solid. So that's one way we have more moles.
And heat is being extracted.
We also added heat, and it's also exothermic.
Yes,
So-
it's releasing energy and things are moving
Right.
and spreading out.
So now let's do for the next one, which is going to be, I'm going to have to erase this because I don't have room to write. So say goodbye. So for the second one, we're going to have delta S is equal to a negative, and that is 778 kilojoules per mole. And if you wanted to just go ahead there and make that into joules, you can. I just like to do it at the end. It's just for some reason, my preference. Divided by 298 gives me a negative 2.61 kilojoules per mole K. Guess what? I know how to do that in my head. So negative 2610 kilojoules, not kilojoules, joules.
Disorder has.
So disorder decreased. Which, if you look at the moles, that doesn't make sense, but it was an endothermic reaction, meaning I had to put energy into the system to make that happen. And I'm going from a compound to an element. So that is something got to look at there. So there I have SB406. I have 1 mole of that, and I'm turning that into 4 moles of an element, which is definitely more ordered than a compound. Does that make sense in your heads? Compounds are going to be more disorder than an element. Remember, elements are the simplest form that something can be in. In a compound, it's not. It's got electrons connected to it. An element is always going to have more order than the compound.
Okay, I kind of see it because like the element has its bonds and its.
But it's just, I mean, there's also...
Spread out.
All right, so entropy summary, we already said that. Positive means more dispersal or more disorder, however you want to look at that. And delta S is less if it's negative, okay? When a reaction, whether a reaction will occur spontaneously or thermodynamically favored, may be determined by looking at delta S of the universe. So here is this little thing here you need to remember. Right there, okay? The system plus the surrounding equals the universe, okay? If delta S of the universe is positive, then the reaction is thermodynamically favored. And if it is negative, then it is not thermodynamically favored. Now, that is just if we're looking at entropy all by its little self, okay? If you're just looking at entropy. However, most of the time we're not just looking at entropy. We're looking at entropy and enthalpy and putting them together and figuring it out. Because there are times when delta S is negative, but if delta H is really, really negative as well, then it could be thermodynamically favored, which is what we're going to do with Gibbs free energy in a second. Or maybe tomorrow. We'll see how far we get today. Is everybody with me? Y'all like this better than equilibrium so far? Well, also by the time we get to acid-base equilibrium, we've done a lot of equilibrium and you're just really tired of it. I get that. All right. So consider this reaction. When we ignite that, the reaction happens really fast. But if you look at the entropy of the system, it's actually negative, okay? Because your H2O molecules are more ordered than your diatomic ones. You're going from 3 to, oh, that should be a 2 in front of that H2O. They didn't balance that. Shame on them. Put a 2 in front of H2O. They didn't balance it, okay? Therefore, the entropy, well, maybe, why are they saying 3 to 2? Oh, 3 to 2. Yeah, they said it, but then they didn't write it. Y'all see that? Mm-hmm. There. Oh, that's in let's not do it in highlighter. So you're going from 3 to 2, so you're definitely getting more ordered. However, if you look at the delta H value, it's very exothermic, okay, which is going to increase your chances of being thermodynamically favored, okay. So the first law of thermodynamics demands that this energy is transferred from the system to the surroundings. So note that the change, increase or decrease, is a result of the energy flow. So if you look at delta S for the surroundings for that reaction of water, for the surroundings it becomes positive. Not for the system, but for the surroundings. So then if you have those values, the delta S of the universe would still be positive, because the surroundings is much more positive than the system. Fun stuff. Now we can find the delta S for, I get ahead of myself sometimes, I'm sorry. That's what they're doing there. So now you can find delta S for the universe and it's positive. So then the system is thermodynamically favored, and it's because of this, because it's extremely exothermic. So the sufficient exothermicity, did you even know that was a word? Offsets the system ordering. That makes you sound really smart if you say that. In other words, sufficient exothermicity offsets system ordering. Don't you sound smart? Huh? You either sound really smart or really nerdy. Which one is it? You sound pompous. Yeah, I want someone to put that on a test. Sufficient exothermity. I can't even say it.
Big words just to sound smart.
I don't have to say big words to sound smart. No, I'm just kidding. What is free energy? Didn't your mama say you don't get anything for free?
No.
The calculation of Gibbs free energy is a way that we can put all this into an equation and figure it out without having to just say, oh, well, this one's really exothermic, this one's really more ordered, which is it? So you can throw it into this equation, okay? A negative sign on delta G means we are thermodynamically favored, which is like delta H, okay? Delta H is negative, it's usually thermodynamically favored. Delta S is the oddball, because it has to be positive for it to be thermodynamically favored. So kind of try to remember that in discussions. The delta H and delta G, when they're negative, they tend to be, well, when it's delta G for sure, delta H and delta G need to be negative, delta S needs to be positive. Sometimes that gets people backwards in their head. There's several ways that we can calculate delta G, and we're going to do them all. Here is the Big Mama verse 3. Delta G of the reaction is equal to summation of delta G products minus reactants. So we should have that equation down. So far you can do it for enthalpy, you can do it for delta G, and you can do it for entropy. Luckily, we knew how to do that very well from enthalpy, so we just changed values, okay? Also, for both delta, we looked this up in our table. For elements, both delta H and delta G are 0, okay? The only thing that's not is entropy. So basically, entropy is the oddball out, right? It's the only one in a different unit. It's the only one that's a different sign. It's the only one that's not zero. So entropy is a weirdo. Or it's unique, however you want to look at it. Okay? All right, so let's look at this. This is the granddaddy of the equation. This is the one that is going to help you the most. There we go, right there. Delta G is equal to delta H minus T delta S. Okay?
So does it determine if it's thermodynamically favored?
Yes, because we can plug in our values and get if our delta G value is positive or negative.
Okay, so
Okay?
delta G is-
The other thing that I want you to remember is, because this is something it likes to ask, it likes to ask you, at what temperature would it be thermodynamically favored? Okay? At what temperature? So what you do is at equilibrium, you know that delta G is 0, because I told you that earlier. Okay? At equilibrium, delta G is 0. So you can substitute that right here. Okay? So then you can do your algebra, and ultimately you can use this equation right here, which will come in handy. So if you want to solve for what temperature it becomes thermodynamically favored at, you do delta H over delta S. So highlight that, put a star by it, make a note saying that's important, because a lot of kids forget that, and that likes to show up on AP questions.
What if it's not,
They usually won't ask you, well, then you're just solving, then you put your delta G value in. But for some reason, when they say find out what temperature it would become thermodynamically favored at, so that would be like the minimum temperature, then G is going to be 0, because you're at equilibrium, it would be
okay.
spontaneous. But for some reason, they forget this little part right here, and then they don't know how to, or they don't know what value to put in there, so they get stuck. So I'm telling you, when they say those words, find out what temperature something is thermodynamically favored in, set it to 0, and then T is equal to delta H over delta S. Yes.
Is it always 0 at equilibrium?
Delta G is always 0 at equilibrium. That is what it's defined at. Just like when we were defining K, we said K is equal to 1 at equilibrium. Well, delta G is equal to 0 at equilibrium. Okay? So that's going to be important.
Wait, K, which one's K?
K is your equilibrium constant.
Oh, okay, that one.
Donald, you're scaring me. We just did 3 units over it, and you're asking me what K is. It's the equilibrium constant. My heart just broke a little bit, Donald. Okay, so Hess's law of summation, remember when we did that? And remember when it was delta H, we were reversing the sign. If you need to reverse the equation, then you also change the sign of G, just like what we've done before. Okay, so underline that and cross off common moles. If you double an equation, you double the delta G value. So just like we did with delta H, okay, just like that. If you have a reaction, then you half the value of delta G, okay. This is another equation that we're going to use. I told you we're going to do them all. We're just going to give you all the equations, and then we're going to work problems. So I'm going to try to get through this today, and then maybe tomorrow we'll just work the rest of the problems in the notes. So this is called delta G equals negative rat length. It's been referred to as rat length for as long as I can remember. Here is the problem that you need to make sure you know is, since we are dealing with energy, we need this as an R value. Do not use 0.0821.
Oh, God.
So 8.3145 joules per mole times K. And then there's that K you said. What's K? It's your equilibrium constant. So that comes back up. Hopefully we remember how to calculate those. Products over reactants raised to their coefficients, right?
Yes.
Okay.
I remember, I just forgot that the symbol was K.
Yeah, you scared me for a
I
minute.
remember everything else.
Okay, good. That makes me
I
feel
just forgot
better.
the
My
letter.
heart's not quite broken anymore. Okay? In the case, the system's at equilibrium, and K represents equilibrium under standard conditions. I don't know if you remember, standard condition is 25 degrees Celsius, 1 atmosphere, 1 mole.
Oh,
Do
yeah.
y'all remember that?
Yeah. Wait, why is it 25 again? Why is it not like...
Standard conditions is not standard temperature.
Okay.
Standard conditions is basically room temperature.
Okay.
Yeah, standard temperature is your 0 degrees Celsius, but we're not dealing with gases on this one that much. Well, sometimes we are, but we're, okay?
We're just doing like earth.
Yeah.
Fully normally expressed.
So there, just to remind you, K is products, reactants, wait. It's not reactants over products.
Products over reactants.
What does your note say? Is it wrong in here?
Yeah, that's wrong.
What? It's products over reactants.
Yeah.
What the heck?
They're making all kinds of mistakes today. They
Brr.
didn't balance the equation. They did.
Yeah, products over reactants. Yeah, switch that in your notes. Bad, bad, bad. Remember this politically correct, okay? Again, when you're using that R value, you want to use the 8.315 there. Okay? So that's something to recall. That's all stuff we've already learned, but I'm hopefully reminding you of that. Okay? And then I think we're almost ready to start working problems. Almost. Okay. There's one more equation, because it's fun to do all these equations, and that's I call it the knife equation. Delta G is equal to minus NFE naught, which we have not learned E naught. That's electrochemistry, but we have to bring it into play here because there's some overlap, and it's N is your number of moles of electrons. We probably actually may not see this till we get to electrochemistry, but it gives free energy. So E is the number of moles of electrons in a redox. F is Faraday's constant per mole of electron, and E is the standard cell potential for the electrochemical process. I'm hoping that doesn't show up in this unit until we get to electrochemistry, which is our last unit, and then we'll bring delta G back into play. So if something shows up on the homework that way, I don't think it will, but just kind of ignore it. And if I see that it shows up on the test, I will mark it out, because I don't want to try to do that until we learn what all that other stuff means.
So that whole equation.
I think they're putting it here so you know that it's there, but I don't actually think it shows up in the work, because we haven't learned how to calculate some of this stuff yet. That's our last unit.
Do we start doing Coulomb's law?
Coulomb's law, yeah, that's the last unit. Okay, so here we go. Should we work this one? Do we have time, or should we stop and work problems all tomorrow?
Let's do it tomorrow. We're going to be procrastinators today.
Okay, so we will start. I think the rest of the notes is just problems, right?
Yeah.
That way you have one thing of notes, and then you have another video with just problems.
And then our